how it's going? This is Harish Dalal and welcome to our channel CodeChef. So the problem today I will be taking is tree difference, the code for which is TREDIFF. It is an easy medium problem from practice section, and the prerequisites are you should be familiar with pigeonhole theory and trees. So before we get actually started, here is a reminder to hit the subscribe button if you haven't yet already. So here is the problem definition given. You are given a tree with n nodes which is numbered from 1 through n. For each valid node I, node I has a value of ai. Now you should answer q queries. In each query you are given two nodes a and b, and let S denote the set of all nodes on the simple path between the nodes a and b, including those nodes. Find the minimum value of absolute value of ax minus ay over all pairs of xy which is present in the set of all the nodes, such that x and y should not be equal. So let's take this let's understand this question first. So let's say this is the tree given to us, and these are the nodes, and these are the value of ax. The particular the red colored are the value of ai of the nodes. Now let's say the query given is 2 and 3. So this and this, we have to take all the nodes in the simple path from 2 to 3 and find out the minimum difference of ax minus ay, which the absolute difference of ax minus ay. So in this case, the nodes which are present in the simple path of 2 to 3 is this one, this and this. These three nodes are present in the path of 2 to 3, and their value of ai is 2, 2 and 4. Hence the minimum difference you can get here by subtracting two ais are the first and the second one. So you will get the difference here as 0. Let's take another query. If we are given ai, we have given the first node as 6 and the second node is let's say the 1, then the simple path from 6 to 1 will be 6, 2 and 1, and the values of ais are 1 to 4, 1, 2 and 4. So the minimum difference you can get here by taking any two nodes. The value of any two nodes here will be 1 and 2, because the difference here you will get will be 1. Hence you have to answer q queries for this particular tree. So these are the constraints given, and can be up to the range of 2 to the 10 to the power 5, 2 into 10 to the power 5, whereas q as well, and ai will be just 1 to 100, and a will not equals to b. So let's start this problem by going with a brute force approach. So you are given two nodes a and b. So what you can do is you can start with a single node a and go till b by using DFS or BFS, and collect all the nodes in the path from a to b and store them in a array, all the nodes in the array, sort them so that they are in ascending the order, and the minimum difference of any two nodes will always be any two adjacent nodes in the sorted array. Let's take an example. Let's say 7 and 5. So if we start with 7 and go till 5, then all the nodes which are present in the simple path will be 9, 1, 2 and 6. Those are the values of the nodes, and if we sort those, that will be 1, 2, 6 and 9. So it's obvious that the minimum difference you can get with two nodes will always be adjacent, either these two, or it can be these two, or it can be these two. So here you are getting the minimum value as with these two nodes, which is just 1, and hence the answer for this query will be 1. Now for this, with this approach, the time complexity will be, for each query it will be O of n, as you are traversing the whole tree to find another node, and there are q queries, so the overall time complexity will be q times n. Hence this is not efficient for this problem. It will give you TLE. because the range of q is also 2 into 10 to the power 5 as well as for n. So we cannot go with this approach. So the next approach we can go with, the efficient approach we can try, is instead of traversing the whole tree, what we can do is we can maintain their heights. Let's say if we got 7 whose height is, if we start from the 0th level, and this level is the first, this level is the second, this level is third, and the last level is fourth. So if we maintain the height, and if we got query as 7 and 9, so those two nodes are on different height level. As you can see, among 7 and 9, the 9 is at level 4 and 7 is at level 3. So make sure to first of all make both nodes of equal height. So here in this case both are of different height, and as you can see 9 is much lower than 7, so you have to make 9 to similar height as 7. So you have to go a parent up of 9 and you will reach to node 8. Now 8 and 7 are at the same height. Now start going up until you find the same node. So at level 3 those are not same, so you go by one level up. Again 4 and 5 are not same, again you go a level up. At last you will reach to node 3, and that is same for both the nodes. Hence, while traveling such path you can store the values as well, and hence you will get the values without traveling the whole tree. And you can store those values in an array again and sort that array, which I mentioned just before, that we can sort and find the minimum value which will be adjacent in the node, one of the adjacent values in the node. So still this method is not efficient, as it is possible that all the queries are at the bottom level of the tree, and we have to travel till the root to get to the same node, and this will again can cost us O of n. Let's say our tree looks something like this. So these are all the n nodes, and we got the query as this and this node. So we do have to travel whole tree again to reach the root node, and still here if every query looks like this, then it will again be q times n, and hence this will give us TLE as before. So this is also not the most efficient approach for this problem. Like, what can be done to make this approach efficient for solving this problem? There is a slight change which we can do to make this particular approach, which I just mentioned, efficient for this problem. So as I mentioned that the prerequisite is pigeonhole theory, and for this problem you have to look at the constraints given. This is most important in this problem, as well as in any problem. You should look for the constraints, and you can get some hints like why those constraints are given like that. So here you can see the values of each node, the AI is just from 1 to 100, and it cannot be greater than 100. So it defines that. So the obvious thing here is that, let's say from my node A the path is something like that to node B. This is my path. Let's say this path contains more than 100 nodes. So let's say if this path contains more than 100 nodes in my path, then it is obvious that two values will be repeating, because according to pigeonhole theory, if there are n holes and m pigeons and holes, and if we have to put each pigeon into the holes, and if pigeon is greater than n, let's say if pigeon is greater than n, the whole, sorry, if pigeons are greater than the holes, then it is obvious that one of the hole will contain more than one pigeon. So these are the holes, and we have to put like 5 pigeons in 4 holes. So first we can start by putting one into this, then second into this, third and fourth. Now each hole contains at least one pigeon, and finally the last pigeon will go into one of the hole. That's why at least one hole will contain more than one pigeon, hence it will look like this. So this is similar as here. There are more number of nodes. Nodes are greater than 100 in the path from A to B. Hence there will be two values, at least two values which are repeating. And we have to find the minimum value of AX minus AY of any two nodes. So we can directly take those two values. We don't have to care about which two values are repeating. We just know that there are two x present, like there will be at least one x similar to another x somewhere, and we can take those two to make our AX minus AY as small as possible, because 0 will be the minimum value we can get, because below 0 we cannot get any value. So x minus x we can give to be 0. So with the help of this particular concept, what we can do is we can start traveling over both nodes unless and until we reach the equal node, which is also termed as LCA here, least common ancestor, which is the node which is the common node for both A and B while going to root. So we start with the lowest node and we go until the levels of A and B are equal. Now the thing here is, as we are going up, as we are traveling up in our tree, as soon as our array, the array of the values which we are storing while traveling up, as soon as the size of array gets greater than 100, it means that now our path contains more than 100 nodes. And as I just explained, that if our nodes are more than 100, then there will be two values, there will be two exact same values in our path. Hence, while traveling up, we will store our nodes values in the array and keep checking whether our array size is greater than 100 or not. If it is greater than 100, we'll directly break out of the loop. We don't have to travel it until the LCA as well. So how does this help is, we don't have to travel in this case. Let's say this is our tree again, containing n nodes, and we have given these two nodes A and B. We don't have to travel till the LCA or the root. We can just travel unless and until our array size is 100 or less. So the complexity reduces down from O of n to O of 100, because we are just traveling at most 100 nodes in our path, in our DFS traversal. Hence for each query it will be O of 100. So the overall time complexity will be Q times 100. And this is efficient, and this can be done in the time limit given. So let's jump to the code now. So I have taken t test cases for the input, and this is my test case function for performing each test case. Now the test case will contain two input, n, which is the number of nodes, and q, which are the number of queries we will be getting. I'm creating this tree, initializing this tree, as well as the cost vector. I'm taking the input for cost. First of all, the cost is the AI value for each node, cost of I plus 1 contains the AI value for ith node. I'm taking the tree test tree as the input. Now I'm creating a parent vector as well as the height vector. So I have to fill up this parent and height vector first of all with a DFS. So why we need a parent vector is because, as I mentioned, if we have to travel up to reach the LCA, we have to know our parent. The parent of like 7 is 4, the parent of 4 is 3, so we have to know the parent, as well as we have to know the height of our nodes, so that we can first of all match up those heights and then start traveling both together till we reach the LCA, which is least common ancestor. Hence we have to know the heights as well. So I'm performing a DFS. Now let's go to the DFS. I'm passing the tree, the current node, the parent of my current node, the node, the height of the current node, and the parent vector as well as the height vector. Whenever I'm reaching the current node, storing its height as well as the parent in their respective vectors, and traversing through their childs, through its childs, by increasing height by 1 for every child. Now after performing this DFS, now I have parent as well as height vectors. What I will do is I will perform the queries in this while loop. For each query I'm getting two variables a and b, for which I have to output the result. I'm creating a vector st to store my all the nodes in the path of a to b. So as I mentioned, if the height of both are not same, we have to make the height same by traveling the lowest node to match up the height of the upper node, so that we can start traveling those till we reach the LCA. Hence, if my height of b is greater, I'm first of all swapping to make that the height of a should be greater. Now while height of a is not equals to b and the size should be less than 100, I'm pushing the cost as well as making the current node the parent of the current node. So after performing this particular while loop, both the nodes will be at same height. Now I have to I have to travel one by one till the top until we reach to the LCA. So until our a is not equals to b, which is the LCA. So the size should be less than 100, as I mentioned. If the the size of st becomes greater than 100, then we don't have to travel anymore. We can break out of the loop directly, as we know now that our path contains at least two nodes having the same value due to pigeonhole theory. Now I'm traveling both nodes until we reach LCA by pushing the cost to the ST as well. Now after performing this, I am pushing the LCA cost to the ST as well, because we break out of the loop if both the nodes are same. We still have to push this particular node cost into the set, the vector. After that, I will check whether the size of my ST is greater than 100. If it is, then it's obvious that two nodes contain the same value, and we can take those two nodes to get the minimum answer 0. Else, if the size is not greater than 100, then we have to sort the array and iterate through that, and always take any two adjacent value who is giving the minimum answer, and finally printing that answer. So let's submit this code. So you can see I got TLE on my second, the larger test case. What I can do to prevent that is, instead of printing with AND which flushes out the output directly, I can use the /n, \n, similar here. Now let's submit this again. As you can see, it is taking more than 2 seconds. Now submit again. Now yeah, it is all correct now, and it took less than 1 second now, as the time limit for this question is 2 seconds. So you can keep track of this kind of mistakes. You can like use /n instead of AND so that it doesn't flashes out the output directly to the screen. So the common mistakes for this question you can avoid is, as I mentioned, you have to break out as soon as the size of vector increases by 100, else it will give you TLE, as you will be traveling whole tree and it will give you q times n time complexity. And use /n instead of AND